Thanks very much, Shota, for the kind introduction and for to the organizers inviting me to give this colloquium. Yes, I guess these colloquia are to try to bridge bridge the gaps between the different communities who are here at Aspen, and so it's indeed a privilege to be talking to people who are in some sense on the phenomenological side of the same set of ideas of gauge theories, and so hopefully you'll have more than a passing cultural interest in trying to see how some of us are trying to understand gauge theories from the point of view of string theories, and trying to understand them from a more first principles approach. And so that's the goal of the talk here, to at least try to convey to you why this is important, why and how one might go about doing this. So the broad overview is, I'll first give a little pitch for gauge string duality, why it's something that has sort of kept a whole community of people 3 decades now trying to understand what the so-called ADS CFT correspondence is really teaching us, and then I'll try to sketch a program which I've been sort of slowly building on trying to start from the quantum field theory, the gauge theories, and thanks. The quantum field theories, which, as you know, are theories of point particles, and how you can kind of naturally bring out a theory of strings or world sheets from a large N gauge theory in particular. And I'll in the last part of the talk, I'll try to give a sort of a proof of concept of these ideas in some sense, how you can, in a particular case which Shota mentioned of the ADS3 CFT2 correspondence, one can go from field theories to the string theories, independently see how the string theory reproduces what you what was sort of proposed from the field theory side, on how you can kind of bridge these two subjects. So, and then finally I'll close with some outlook. So the first part is very general, so my apologies also to the members of the string program. This is all, much of it will be boring for you. But just to set the stage, we all know that quantum field theory and general relativity have been sort of the mainstays of 20th century physics. They're very broad theoretical frameworks in some sense, and between them they describe most of what we know about our universe. So quantum field theory, as you all know, especially in the guise of Yang-Mills gauge theories, describes essentially all the non-gravitational forces at the quantum level. But it's also a very versatile framework which has been used in number of different areas, and I just listed some of them here. And general relativity is a classical theory, but it's a very effective classical theory that has described gravity, of course, as spacetime geometry, and in particular it's the best description we have of at the very large scales, and enabling us to develop this picture of the evolution of the universe almost all the way until the Big Bang. So these are two very well established sort of paradigms of physics, but string theory is an ambitious framework. Again, I view it as a framework rather than any particular instantiation of a particular theory. As a framework, it generalizes quantum field theory to also include gravitational interactions at the quantum level, something that quantum field theory is famously incapable of. I won't sort of need to tell you very much about what string theory is beyond some very bare bones, but just a few salient facts. what string theory essentially exploits is the fact that the rather remarkable fact that if you consider a relativistic closed string, it contains amongst its excitations the graviton as one of its lowest modes of excitation. And you can develop a perturbative theory of the interactions of these closed strings, which generalizes our idea of perturbative field theory amplitudes in terms of Feynman diagrams. And now the Feynman diagrams are sort of world sheets, these two-dimensional surfaces traced out by, in this particular case, closed strings. So the basic framework of string perturbation theory, as it's called, is very similar to what you do for QFT perturbation theory. Instead of Feynman graphs of this kind, you have now surfaces, and these surfaces can have, instead of the loops that we have in Feynman diagrams, we have these holes or handles in the world sheets, and the interactions of the string theory can be given in terms of certain Feynman rules on these world sheets, and the expansion in quantum field theory, we typically expand in a sort of the quantum expansion is a loop expansion in the number of loops in Feynman diagrams. Similarly, the quantum expansion in string theory is in terms of these handles, these holes in the world sheet. So that's the loop expansion, and the loop expansion parameter is essentially the Newton constant. It's or what is sometimes called the string coupling, the dimensionless quantity. So this object GS denotes the string coupling, and this factor of GS square or the G Newton weights the genus. So just like Planck's constant weights the perturbative expansion in a quantum field theory, or for that matter, the fine structure constant or the QCD coupling constant. In string theory, these diagrams, which come with higher and higher loops or genus, are weighted with powers of the Newton's constant or G string square. And as Feynman prescribed, you sum over all possible world sheets to get a string amplitude. So the structure is very similar to that all of you are familiar with in quantum field theory. So just to give you that initial sort of introduction to what string theory is, but the thing that really is the central topic of the talk today is this very completely unexpected, when it came about nearly 3 decades ago, due to the work of Maldacena, this completely unexpected equivalence between string theories, which give you a consistent theory of quantum gravity on a certain class of spacetime, and large N gauge theories, so conventional Yang-Mills theories, but in the so-called 't Hooft large N limit, living on the boundary of that spacetime. So this is perhaps many of you have heard talks on this ADS-CFT, and so you may be familiar with this representation of the spacetime in question over here. These are some kind of hyperbolic spacetimes or anti-de Sitter spacetimes, which have this tin can-like representation. The cross sections are sort of spatial cross sections are genuine hyperbolic spaces, and the whole spacetime is a solution to Einstein's equations with the negative cosmological constant. So, and you can kind of represent it, you can kind of conformally represent it in terms of this finite cylinder. It's a solid cylinder, and the boundary is the boundary of the cylinder, or the conformal boundary of the spacetime. And so this correspondence is between all the quantum gravitational phenomena happening in the interior with the boundary, with observables on the boundary. And in fact, this is a very precise a correspondence in which questions of quantum field theory get translated to questions of string theory or gravity, and vice versa. So there's a dictionary, and it's what is called a holographic dictionary between the bulk and the boundary, and typically the most typical cases are where the boundary gauge theory is a conformal field theory, and so CFT in d dimensions, the d-dimensional boundary of this d plus 1 dimensional anti de Sitter spacetime, which is often referred to as the bulk, so there is a holographic dictionary between the bulk and the boundary, between which I'll just say give you a few elements in that dictionary very shortly. So you can translate questions in quantum field theory to those in string theory. But one of the things which I will emphasize here is why this is there are many reasons why this is a duality, but one very striking reflection is the fact that weakly curved anti de Sitter spacetime, that is when anti de Sitter spacetimes with very small curvature, so they can be described very well by Einstein's theory, those are related to strongly coupled quantum field theories, precisely the regime of quantum field theories which we normally find difficult to access with conventional techniques. So that's been one of the very remarkable features of ADS-CFT, and what has been exploited, especially in the context of applying it to other areas, that you can describe in terms of classical gravity many of these questions about strongly coupled quantum field theory. So it's rather remarkable that very strongly coupled large N gauge theories can be described have a purely classical description in terms of Einstein's equations, at least in some limit. But there is a lesser known sort of converse to it, which is also equally remarkable, which is that a highly curved anti de Sitter spacetime, that is one where the curvatures are very large in the appropriate units, a very highly curved anti de Sitter spacetime, so its dynamics is very far from being described by Einstein's theory, but it is captured by something that all of us have studied in our quantum field theory courses, namely perturbative or weakly coupled quantum field theory. So that's something you think should also get you a lot of mileage, because you know what weakly coupled quantum field theories are very well, and that's enabling you to tell something about anti de Sitter spacetimes, which are very far from being understood by Einstein's theories. So I'll elaborate on this a little bit and tell you a little bit about this dictionary. So it's, as I said, a very precise statement about the equivalence of two different presentations of a quantum theory. One is this gravitational description, or the quantum gravity stringy description, and the other is a quantum field theory description. And the Hilbert spaces, it's an equivalence of Hilbert spaces on both sides, in which operators on the boundary, gauge invariant operators to be specific, are mapped to correspond to states in the bulk, physical states in the bulk gravitational space-time, and in particular the dimensions of these operators, which in general would be not just their classical dimensions, the dimensions of operators correspond to the energies of the state in the bulk space-time. And you can go on to talk about correlators of these gauge invariant operators in the field theory. They correspond, for instance, a 3-point correlator would correspond to cubic interactions of the bulk theory. And the bulk theory will in general not just be gravity, it will have a whole tower of stringy excitations. So that's, and so on, the 4-point correlators, etc. But the statement I was making at the end of the last slide was one which is sort of more precisely captured by this kind of a dictionary. For most purposes, you need to just focus on two parameters on the gauge theory side and the corresponding two parameters on the string theory side. So what are these parameters? So what Toft taught us about large N gauge theories is that Yang-Mills gauge theories have coupling constant, the Yang-Mills coupling constant. And then there is N, the parameter which signifies the rank of the gauge group, UN gauge theory, for instance. Toft taught us that the appropriate perturbative parameter is this combination of the Yang-Mills coupling and N. So if you want to organize the, to make a sensible large N expansion of your gauge theory, you hold this combination fixed. As you take N to infinity, you take sort of the Yang-Mills coupling to 0 in a coordinated way, such that this thing called the Toft coupling is held fixed. Then you get this additional parameter 1 over n in the gauge theory, which is what Toft exploited as a small parameter, which is different from the conventional small parameter, which is the perturbative coupling constant. So these are the two parameters on the gauge theory side, basically the Yang-Mills coupling, and then 1 over n. And these translate to two couplings, or two parameters on the string theory side. And what are they? Basically, the size of the anti de Sitter spacetime, or the radius in dimensionless, appropriate dimensionless units. And that's proportional to typically a positive power of this coupling. So very large coupling means that the radius is very large, or equivalently, the curvature is very small. And 1 over n translates to this parameter which I introduced when I talked about the string coupling constant, the G string. It's really something proportional to 1 over n. And we will be typically in the context of this expansion, or the 1 over n expansion of the gauge theory, which translates to a perturbative expansion in the string theory of the kind that I showed with all those Feynman diagrams. So these are the two important elements of the dictionary of parameters between the two sides. And this illustrates what I said at the end of my slide at the end of my last slide, namely a strongly interacting quantum field theory, one where this coupling is very large, corresponds to the radius being very large, or equivalently curvature being very small, and hence describable by Einstein gravity with maybe some corrections. So that's the side of the duality, in fact, which has been very much explored. But then you could equivalently look at the weak coupling quantum field theory, where you apply perturbative techniques of quantum field theory, and that corresponds to the radius being very small, and hence a highly curved ADS, or what you might call a stringy geometry. So that's I'll come back to these parameters shortly. But that's just to give you an idea of that. There's a very precise correspondence between parameters on both sides. Now, why is this such a big deal? Both from the GR side as well as the QFT side, I think this came as quite a remarkable sort of. It gave you remarkable insights. From the GR side, it gave obviously a very concrete proof of concept of what a quantum gravity theory would look like. I think it's the first, albeit in a class of spacetimes, but it's a first example of a very concrete description of what quantum spacetime in say these asymptotically anti-de Sitter spacetimes would look like, and it realized an earlier idea of this holography between the boundary, where the theory on the boundary was effectively capturing all the local physics, seemingly local physics in the bulk, and this description on the boundary was in terms of a very familiar quantum field theory. So it was a very beautiful realization of this old idea. So from the GR side, that's something that, again, people have been trying to decipher what this holography really, how it really captures the physics of gravity in the bulk in terms of how it's encoded in the boundary theory, and that has been the subject of a lot of investigations. It has also shed light on questions about the black hole information by looking at black holes in asymptotically anti de Sitter spacetimes, for instance, and describing them in terms of the quantum field theory on the boundary. So those are things I will not have time to talk about, but from the gravity point of view, it has given a lot of insights. From the quantum field theory point of view, as I said, gives a very a very remarkable description of strongly interacting gauge theories in terms of gravitational physics, especially the ultra-strong coupling. And I saw that, for instance, in the in your Collider program, you are trying to understand very strongly interacting quark gluon plasmas or QCD, so at least in a certain class of quantum field theories, these have been described. You can capture the behavior of strong coupling in terms of gravitational physics, and often just by solving classical Einstein equations. From a more conceptual point of view, it also is a realization of a very old idea that that the lines of flux of a gauge theory really are stringy objects. I think this was there at the beginning of the developments of QCD and so on. Of course, it goes back in a sense to Faraday and Maxwell and Dirac, etc. But in the context of QCD or the strong interactions, this certainly had a very compelling kind of picture associated to it. But in these theories, you can actually realize these ideas very concretely. Finally, I just want to say, I mean, there's always a lot of talk about string theory not being verifiable and so on. Yes, at least in terms of smoking gun experiments, we are certainly far away from it. But at least to, I think, fellow physicists, I'd like to kind of advocate that there's more to sort of falsifiability than